Okay, I think we're live. Alright, let's try this. Hello. So it should be playing. Wait. Yes. Pretty good. Close that. Good. Awesome. Alright. We should be live. We're going to do an audio test. The last time I did this, I recorded for 3 hours and almost none of the audio was usable, so... Round 2. Just going to check what it looks like on YouTube. 1 second. Alright. Sounds good. We'll find out. Fuck it. So, what are we trying to do? Let me show you. So, throw back to the last 3 hours that we recorded for. We want to... Oh, yeah, quite large. So, here's the project. We want to build a ESC for a BLDC motor. Building ESC for BLDC motor. This is the motor. This is something I purchased off Amazon a while back. Here's its peak current. Here is the input voltage range. It's more than 14 volts. I think it's 16, something like that. Anyway, it's 3 to 4S batteries. So when a 3S battery is fully drained, it's around 11 volts. When a 4S battery is fully loaded, it's probably around something like 16 volts. We're going to use generative AI for a lot of this design, and definitely to check our work. Although there are a ton of hallucinations, and we already experienced that in the last episode. We're going to use KiCad to design. I was looking at Easy EDA, but their server was down, which is sketchy. And JLPCB for the PCB assembly. That was in part why I picked Easy EDA originally, because it ties in with JLPCB really well. I also don't think it's JLC. And here are the parts that we've selected. So we picked a motor driver, it's about $2, and a microcontroller, that's also about $2. I imagine that's USD. And we're going to use that to design this ESC portion, which is going to go between the motor and a flight controller. The final goal is this. 1 second, let me go and grab my drone. This is what we want. So I have a beautiful nano quadcopter. It's supposed to be under 250 grams. I doubt that. I think it's closer to 350 right now. It has quite a large chunky battery. This is the motor, and this is an ESC or electronic speed controller. And so we are designing to replace that part. Right now, from what we picked, it looks like we'll be able to do that pretty easily. Although now that I've said that, it's just not going to work. Cool. So yeah, the idea, design the ESC, and then the next step is going to be to redesign this entirely. So it has currently 2 layers of PCB. It's quite heavy, so we want to get rid of that. There's a bunch of metal. Yeah, you can see these metal standoffs here that separate PCB top from PCB bottom. That's really heavy. There's no point in having that. It'd be really nice to get under 250 grams. And there are a couple other things we can get rid of, like I have this microcontroller. Oh, you can barely see that. There's this microcontroller standoff too. This is something I'll have to get better at showing stuff on video. Anyways, ESC, electronic speed controller, where are we? So we have the data sheets open here for our 2 key parts. I'm going to show you KiCad. This is what we have so far. So here's the MCT driver. I've connected a bunch of things up. Here is the motor controller. Sorry, here is the microcontroller. So it's an MSP430. Again, we picked it mostly because it's cheap, but also because I do know how to program these things. I had prior experience. And these are the steps we want to take. So connect the microcontroller to the driver, the flight controller to the microcontroller, and we probably won't get to steps 3 and 4 by the end of the day. Here is what the PCB will look like. roughly, here's the layout or footprint for the driver, and then here's the footprint for the microcontroller with right now a couple of resistors, 0402 metric footprints for your viewing pleasure. All right, where do we want to go with this first? I'd say let's do step one, finish the microcontroller to driver connections. So the way that we're going to communicate with the driver is over SPI. So the microcontroller has these SPI pins, 21 to 24. Those connect to their respective counterparts on the driver, 35 to 33 to 36. We also have a series of GPIO, break, fault, sleep, and drive off. So turn the driver off. These are interrupts, so when the driver experiences a fault, it will set that pin high, low. So if this is not a fault, so if it's high, that means if it's a fault and it's high, that means there's a fault, but if it's not a fault and it's high, that means there's no fault. So if this goes low, that means there's a fault. And this is not sleep, and so if this goes low, that means we're not sleeping. I'm not quite sure what that does. We'll go back to that in a sec. So those are GPIOs, and then we have PWM output. This is 200 kilohertz, and it will dictate the rotational qualities of the motor. I guess these signals that are being fed to the motor. Those signals being out A, out B, and out C here. Some other things to note on this driver: there is a buck converter circuit. So this is like which will take the input battery voltage and lower it and provide an output. Right now, you're not powering anything off that buck converter circuit, so you have to have it there. It says that in the datasheet. You can't leave it floating, but we will populate it, but we're not going to end up using it currently. Maybe we'll expose it via a pin just in case we do find something we want to power from it at a later time. We also have a charge pump, which has a series of passives, and that's going to... Charge pumps are normally used as a boost converter to increase voltage, so I'm not quite sure what the charge pump is being used for. We'll have a look at that later when we finish that part of the design. We have this current limiter, so by setting the value of these two resistors or this voltage divider, we are able to decide what the maximum current going to the motors will be, and we know that that needs to be under 6.5 amps. Last but not least, AVDD. This is the power that's going to be... So we're connecting the batteries to the driver, and then the driver is going to have some sort of circuitry to output a 3v3 signal, which we use to power this low power microcontroller. So that AVDD is going to output like less than 5 milliamps, I suspect. At least that's what I've calculated from the MSP430 datasheet. Alright. Sounds good. Let's start connecting. First of all, OBS Studio. Let me see the YouTube Live control panel. In case any of you have questions, feel free to throw them in the chat. Cool. I should also change the name because ESC, people aren't going to click on that. So real quick, let's edit the name, designing a motor controller from scratch. Cool. I think that's slightly better. And then we could probably try to get some people over here. So I'm gonna head to Twitch, look up just electronics. Anybody streaming right now? Channels, live channels, tag, West that plays music. Alright. Nope. No no viewers. All right, who does? Software and gaming. Oh, look, see, engine C++. This could be nice. Just throw something in his chat. Da, 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 da. Let's share this. Something I do not know how to do. How do I share my URL? Restart channel content. Get shareable link. Beautiful. All right. Okay, before I post on this guy's channel and steal some of his subs, I'm curious. Is it Twitch? Is it okay to self-promote on someone else's stream? Having a look. Here, look at Reddit with me. Like it's 99% of the time, no. Never self-promote unless given the express content of the streamer, and never ask it's okay. Self-industry, it's a sure way to be alienated from those communities. Okay. Okay, so just go and self-promote. Okay, I won't do it then. Maybe we have to get creative with this. Okay, let's focus on the technology. We'll get back to the stream work later. Okay. So microcontroller driver connections. What do I need to clear up? I think let's clear up this SPI first. So let's say that. Here. So SPI. Pop over here. Have a look at the detail description, feature description. Pop over to, I'm sure SPI is here. Nope. SPI communication, programming. Okay, so what am I specifically not sure about? I know that S-Clause is UBCO, right? So it's not the MCT I need to worry about, it's this MSP430 portion that I'm a little curious about. So, detailed again, serials, peripherals, enhance universal serial communication interface. All right. So supports SPI and I2C as we expect. Both support SPI 3 or 4 pin. Cool. Anything else? So this is section 6.10.7. Okay. Cool. Okay, I want to know more about the pins. We'll probably need to go as far as in the user manual to learn more about this. Well, let's start with the I/O. So this is, we're looking at pin 1.4, 1.5, 1.6, and 1.7. Here. 1.4 to 7, here you go. So we have the selection logic. There's nothing here that's out of the ordinary. Okay. I think it'll be worth our while to go to the user manual. I mean, what am I worried about? Is it the, do I need pull-ups or whatnot? It does tell me here, the application implementation. If I look at the SPI lines, not here. Okay, so just There you go. Primary for the. So this is for the ZR, and this is for the ZT. Which I thought we had the ZT. Oh, this is totally unclear. Wait. So Z0TR. That doesn't help. I think I have it. So Z0TR. So which one is it? Oh. So there is Z0R and Z0T. So I get the impression that this is definitely a ZT product. Which am I using here? This is Z0T. Oh, yeah, like this. What? Okay, let's go back to pins. This is slightly annoying. These little variants do get me. So if we're looking at the SPI pins, which I guess the S clock, SDI here, but on the ZT model are replaced by DIR Advanced LW. And I said, and so it's really important I know if I have the ZT or the ZR. What I did, let's see if it can. So this has the SPI. So this tells me it's the R. That's my understanding. Okay, and you know I really want to write this down. So for this variant for this is okay for the PCB for furnace symbol on the aforementioned GLC PCB PCB website. Okay, just a reminder for myself that we are in fact dealing with the ZR variant. Very important, don't want to make that mistake. Okay, so SPIs for sure, cool, that's confirmed. We will just have a quick look at the connections. Do we need to throw on any pull-up resistors? Doesn't look like it, it's just straight through. Okay, so SPI is done, pretty confident that that will work. Now let's have a look at the others, fault N and sleep N. And fault. Oh my goodness, so many references. Okay, I'm gonna go back up. Is there any way for us to know for sure what does and does not require a pull-up? So and fault indicator, pulled logic low with fault condition, open drain. Okay, it's open drain, perfect. Requires an external pull-up to external supply is used to pull up. And fault, ensure that is pulled to at least over 2v2 on power up, or the device will enter test mode. Cool. Okay, so let's have a look at the microcontroller data sheet. Does it tell us if we can enable an external pull-up resistor within the MSP itself, so that we don't need to add an extra one on the board? Let's just look up pull up. Pull. Let's try pull. Damn it. disconnection of unused pins. Here's how you do that. This will be very useful in the future. Alright, does not look like there are any internal pull-up resistors, and we can double check that by asking ChatGPT. Does this one have internal pull-up resistors that can be enabled, software enabled? No, it does not. All right, so we need external pull-up resistors. Awesome, glad we know that now. So let's go to end fault. We'll add in a 10K external pull-up resistor. So here, see, it's already getting really ugly. This is something I need to learn how to improve. I need to get better at it, so I need to be able to organize. So here, off of these VM pins, we have a couple of capacitors. Those push into this line here that's coming off the current limiter, and then we have fault N, which is now also is experiencing some intrusion. So let's just keep dragging things along. Is this the right way to do things? I have no idea. Let's do that. If anybody has suggestions, I'm totally open to assistance. Thank you. Okay. True. Pull up resistor. Copy this here. Slap it here. See, it's not going to work. I'll put it maybe a little farther here. Wire it up, and then we want to put I'm going to connect it to AVDD. What was that rule? It said, follow the pull logic load fault condition. Open drain output requires an external pull-up resistor to this. If an external supply is used to pull up end fault, ensure that it is pulled on power up or the device will enter test mode. Okay. So I figure we can just connect this to AVDD and everything should work fine and dandy, but that also assumes that AVDD hits 3v3 or is higher than 2v2 before this not fault logic kicks in. Kind of a big if, I'll be honest. Maybe it's worth our while to add a way to disconnect R4 from AVDD in case we do really need to connect it to an external. Although we have no choice. What are we going to connect it to? The 3v3 supply is only coming off of this AVDD. We have no other way. We have no linear regulators on board. You know what? This is one of those decisions you just have to make and live with. So let's label this copy pasta AVDD. Good for me. Okay, that's done. Just drag this over one. Stop it. So the reason you keep seeing that is because drag is G and I keep hitting D, which is data sheet. I think it makes sense. I really don't like this. I think it's not ultra readable, but you know what? Let's move on. Stop looking at it. So here you go. We're gonna move on to sleep now. When this pin is logic low, the device goes into sleep mode, so we can save some power. A 2240 microsecond low pulse can be used to reset fault conditions without entering sleep mode. Okay, so this is an input. Do we need sleep mode for this driver? I guess, you know, we're flying with a pretty limited battery range, so we're talking microwatts probably. Also, yeah, no. So let's say the device isn't flying, the battery is plugged in. It's going to be providing. Okay. And so battery's plugged in, microcontroller turns on. By default, we could say that it keeps the driver in sleep mode until you provide it some sort of PW input. I mean, the microcontroller itself should be sleeping and waiting for it to receive a given pin to receive a PWM signal. So we'll slap and sleep. The good thing is it doesn't need any sort of pull up. So when the spin logic is low, the device goes no. It's an input. It's not an open drain output. So we don't need we would need the external resistor if the microcontroller GPIO pin is open drain, which I suspect it will be. Come back to you 4.4. Let's go find open drain. Just look up drain. Or ask ChatGPT. Okay. Are the GPIO pins open drain? Yes. Okay, that's what ChatGPT says. So the device is primarily designed for metrology and power measurement applications. Okay, emphasizing open drain. So I believe this is a power saving measure. Okay, so external pull up it is. See, we gotta keep just pushing this along. Get rid of that. G for drag, because I'm learning. I can kill that. I'll move this ground. Can I just label this as ground? Is that fine? Stop at. Just want to get rid of this bloody node. Go die. Suit that. Fire it up again. What if I just label this as GND? So find out if this works or not. Ooh, it's kind of cool. No, it's not too bad. I'm curious. Does that VM actually connect? So we're gonna go to our friend the PCB. Hello. And we're looking at the MCT 91011. So 91011. Actually, we're looking for C4, C5, which we don't have laid out. I don't know what this is, but we'll just add a footprint. It will be C underscore or 42. Nope, I want hand solderable. There you go. Done. Convert. Throw that there. So does it connect to ground? It looks like it connects to ground. Okay, awesome. The net name is correct. We don't need that symbol. Cool. Slightly better. Now we just copy this resistor over. Lay it down here. Wire that up. Wire this up again. It's going to. We don't need to wire there. It's going to AVDD. And this this can just be a standard 10K. We don't need to get fancy with this. Yes, it's 0K resistor. That'll work really well. 042 is perfect. No, don't cancel, you cheap slut. Done. 10K. Cool. Cool. Again, see, it's so ugly. We'll draw a couple of these in. Put this one in too. Just make sure everything makes sense. Look, another resistor, good for us. Driver off. All right, what are we doing here? Driver off. Now we have more SPI work. We'll do driver off first and then go back to the SPI in this list. Okay, gonna do a quick audio check before we do this, so be right back. Stay tuned. Back, stay tuned. Ooh, flip resistor, copy this here, slap it here. See, work. I'll put it maybe farther here, wire it up. And then we want to put connect to ABDD. What was that rule? It said follow the full logic load, fall condition, open drain output requires. Test, 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 test. Hello, hello. Test, 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 hello, hello. Test, 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 hello, hello. Test, test. Okay. An external pull-up resistor to the Alright. Oh, still a little loud. So I've tried to fix my audio volume right now. I was at 26 dB, but now at 15, and it seems like it's not crossing into the red too much. Only if I talk really loud does that happen. So let's go through my headphones again. Test, test. Alright. Okay. So we're going to try for another 2 minutes, and I'm going to do another audio check. So, where are we? We are... So we are on driver off, I believe. So the schematic, yep, driver off. Go back to the data sheet, driver off. When this pin is pulled high, the 6 MOSFETs in the power stage are turned off, making all outputs high Z. So we want this to be pulled low. This. That there. I don't know what R5's doing, but bye-bye. We don't need this to be all the way over here. We'll drag it back. Over here. And then this gets the good old ground label. Maybe not. See, that just makes me angry. Fine, we'll add a little wire. Cool. Also, I want this to be ground A, not ground. VM is supposed to be power ground, so ground is fine there. Also, let's see what I have here. I should call this P ground. Let's call a spade a spade. Look at that! Look at these horrible connections. Yeah. Oh, I guess that makes sense. It tells us that the pins are in fact connected. So we'll keep that. And I'll even... See, no, I gotta stop doing that. Leave it alone, Mike. It's fine. Power 1, power 3, ground A. Okay, so they're different. Awesome. Be bad. This is going to be P ground. We're gonna have a quick how do you do on the over here. So where's P ground? Come here. The motors are, here's VBAT, here's P ground. It's called P ground, and we can see that this is connected to P ground. Fantastic. Give me this net. No, let me. Okay, no problem. All right, I'm gonna do a quick audio check. Be back. Again, at the MCT 9, 10, 11. Get driver off, go back to the data sheet, driver off. When this pin is pulled high, the 6 MOSFETs in the power stage are turned off, making all outputs IC. So we want this to be low. This. That's it. Okay. The audio sounds just fine, so we're going to keep on chugging along. What do we have? Fault end, sleep end, drive off, all done. Next, brake. What do you do with brake? Up here, brake is an input high when we want to turn all low side MOSFETs on. Okay. Let's just think about this for a sec. So we have 3 pins that do slightly different things, but are also relatively similar. So sleep will put the driver entirely asleep. It tells us when the pin is low, the device goes into low power sleep mode. So that is a power saving feature. Drive off turns off the driver portion of this chip. So the 6 MOSFETs in the power stage are turned off. So that means we still have access to the communication channel like the SPIs. Okay, and then we have brake, and brake will brake the motor by turning all low side MOSFETs on. I'm curious how the brake, so if we turn the brake on and we have a PWM signal still feeding into the driver, does that cause any problems? Are there any shorts? Because if the low side MOSFETs are on and the high side MOSFETs are on, does that not short battery to ground? I'm sure they talk about that in a brake section. So detailed description, application, blah 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 blah. Yes. Okay, so here there's a detailed design procedure for this three-phase BLDC. So we'll have a look at that real quick. Although if it talks about, it talks a lot about Hall effect sensors, then that's not useful for us. We are not using Hall effect sensors. They are not a part of our motor. We don't need that kind of precision. Okay, so we're looking for brake information. That's functional mode, sleep mode, operating mode, fault or reset, drive off. I want to learn about the brake. See, this is annoying. Just look up brake, whatever. So electrical. Oh. Okay, so on the inside, we do have pull-down resistors. So brake, there's a pull-down resistor internally, so we don't need to add one externally. What about drive off? I don't see drive off here. Is that? No, it can't be dirt. This is the ZT. Where's the ZR? There it is. There's the ZR. So brake has a pull down, so we don't need to add one ourselves. And sleep is a pull down, but we want to pull it up. Now where is our friend? Drive off. DOB off, is it not? We're right now on page 19. Is there seriously no? Go take me back to page 19-ish. Oh. Logic level input pin internal pull down. So the input structure for the logic level pins brake, DIR, drive, and sleep, PWM, and S clock. The input can be with a voltage or external resistor. It is recommended to put these pins low in device sleep mode to reduce leakage current. Okay. There are internal pull-ups too, and there are a few open drain pins. Good to know. And then a push-pull pin. So SDO, that's fine. Slew, we select. We don't care about those. Well, slew for sure. That's not part of the ZR model. Advanced mode, don't care. Okay. This is perfect. This is a great section. So, brake, DIR, drive off, all already have internal pull downs. and ESD protection, which is just magical. So we don't need this external pull down. Bye bye. We will just drag this. Stop it. It's over. What's wrong with you? How do you drag this? Just delete it and redraw, I guess. Maybe. So M is move. That doesn't work. G is drag, and there you go. Break down, right? Break, drive off. Already pulled down. Awesome. S clock, already pulled down. PWM, already pulled down. Where's DIR? DIR must be part of the ZT model, so we don't care about that. And then end fault, FG out. What is FG out? That has to do with the Hall effect sensors, so we're ignoring that. Although we'll figure out later if we can leave it floating or if we have to pull it up. The open drain output really is okay. So an SDO in open drain mode. So SDO will need to be pulled up. So let's do that. See, the problem with electrical engineering is that you constantly need to evaluate the information from multiple places and multiple sources. So the good thing is this is all in one source. The bad thing is that you're looking at like section 1.4 for this kind of information, and then 3.5 for this kind of information, and you have to just mesh it all together. So that, I mean, the obvious benefits of generative AI are that it can take all of that and mesh it together in, you know, a couple of bullet points. The problem is that those AIs hallucinate so goddamn much that you can't really trust it. Okay, and I don't know what value to pull it up with, but I assume 10K is fine. Let's ask Gen AI. What do they think? Go here. What? Well, you know what, I'll just Google it with you here. So pull up resistor value for SDO. Fast performance, we don't need fast. I mean, what does this SPI communicate at anyways? We'll do a megahertz. To say power, larger ohms can be used. So let's just pick 2K. Here is the MSP datasheet. We'll look at SPI speeds. Specifications. So this is the clock frequency. Currents, clock specs. We don't care about that. We want SPI. Where are you? PCO, we don't care. Wake up characteristics, IO ports. Here we go. Should be here. Now, let's look up. I don't favorite this. Okay, here you go. Clock frequency, max is F system. So we'll do a megahertz, whatever. What does the MCT take? Say, if we just look up SPI, I'm sure it'll tell us. There's so many references, specifications. Now, if we look up SPI, the buck regulator, protection circuits. Come on, timing requirements. So S clock minimum period. So the maximum frequency is 1/100 nanoseconds, which is 1 megahertz. That's the max. High, because that's 10. That's probably 10 megahertz. So that would be 1 micro. This is 100 nanoseconds, so 10 megahertz. Okay, no problem. 1 megahertz it is. So we'll pick a 2K resistor. Go here. 2K, done. Done, save. Push that over. Done. Yeah, so we're gonna get rid of all of the silk screens. We're not gonna have enough space for those. I mean, ideally, this is something that we measured on the last stream. So ideally, we take this ESC, which is like 3 centimeters by 1 centimeter, and we're able to make it smaller. So let me rephrase that. Ideally, the ESC that we are making here is going to be smaller than the off-the-shelf ESCs. It doesn't need to be by much, but let's see if we can do better. I mean, we have newer tech. I'm pretty sure this Hobby King, Hobby Bro, whatever the ESC is 10, 15 years old. So, good. We'll drag this over. There we go. Now, I'm pretty happy with brake, SPI, all the Hall effect sensors not being connected. Let's see if there are any recommendations for what to do with pins that you're not connecting. This should be in the application notes down here. So there's layout, guidelines, example. Let's go to guidelines. Separate the SW buck and feedback buck traces with ground separation to reduce buck switching from coupling this noise into the buck outer feedback loop. Widen the buck FB buck trace as much as possible to allow for faster load switching. Okay, and then there's your recommended layout. Cool. What if I do NC? No, too many. Not connected? We can do it. Nope. Yep. We'll go back to pins. Noise filter capacitors may be desirable connected between the positive and negative Hall inputs. Don't tell me much. Go to the Hall pins here. So that's the buck. None of these are the Hall inputs yet. The comparators. Not clear. Oh, here we go. So it should say something about leaving them floating. To be fair, if we go back to that okay, so here we have some disconnects. This is the scenario where you have digital Hall inputs, so the driver doesn't say anything about leaving them floating. Okay. Nothing so far. So we're gonna go back to that place where it told us all about so this pin does that, this pin, there are these pins which have a pull down, these pins have a pull up, these pins are open drain. I think that's going to give us more information and tell us what we can do with these in the event that we want to leave them floating. Just don't remember. Here it is, pin diagrams. Break, NCS, faults, don't care. SDO, slew, VCell, not what I'm looking for. Advance and mode. Oh, none of these are the hull pins. If I get no information from this, I'm just gonna assume I can leave them floating. I might need to do a lot of janky soldering to fix a bunch of this stuff, but it's better to just get it done, get it sent off. Okay, I have no information, so we're just gonna keep them floating. So, done SPI. Although chip select, do I want to... Yeah, chip select's fine. I don't think we need a pull-up resistor for that. We can just have the microcontroller pull that up. Yeah, that's fine. The microcontroller will pull that up. What's that? Oh, let's ask ChatGPT. Should have a external. Should I have external pull-up resistor on and chip select? Yes. Since the GPIOs on this device are open drain, they do not have internal pull-ups. Without an external pull-up, the NCS pin may float when not actively driven, leading to unreliable operation. So is the microcontroller not actively driving that? That's odd. Why would the microcontroller not be actively driving that? Let's ask Chad. Does the microcontroller not actively drive NCS? Only if it's configured as a standard push-pull. However, since its GPIOs default to open drain behavior when configured as outputs, you may need an external pull-up. So if we can configure the MSP430, the microcontroller's output, as push-pull, the controller can actively drive both high and low states. If it's open drain, it can only pull low and would require external pull-ups for high state. Are you using SPI hardware or bit banging the NCS signal manually? Well, that's a great question. I know, so I typically bit bang it, but is the SPI hardware going to work for me in this case? It should. I don't see why not. I'm gonna add the resistor, whatever. I don't think I need it. You know what we'll do? How do I mark this as don't connect by default? I'll copy this, push that there. How do I mark as don't populate? We'll do this in front of you because we're working together. So here, keycad, don't populate. Do not populate. Don't pop. Do it. DMP. How do you do it? There. Yes, 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 yes. All the commercials. Okay, it's getting close to my bedtime. I'll probably do another 5-10 minutes and then call it. Oh my goodness, just show me how to do it. Here, oh, there it is, done. Okay, we go here, we click this, we click do not populate, magic. And we'll make sure that shows up, done, boom. Okay, so that was NCS. We have STO, STI is fine, SClock is fine. The halls are fine. PWM already has a pull down. Drive off, pull down, sleep N and fault, external pull-ups. iLim, I don't know if 10K is the right option here. Let's just stick with 2K everywhere. Don't really have an excellent reason for why I'd use 2K and not 10K. You can always change this after the fact. Okay, done, done, done. I hate this. Why is it so ugly? Move this down, fire this, and then this can drag with this. Done. Little less uglier now. Awesome. iLim, we need to pick the resistor values, which we can do by going to this data sheet, clicking here, going to typical applications, detailed design procedure. So supply voltage, oh, this is not what I care about. Cool. Operating at lower voltages generally allows for more accurate control of phase currents, so we're going to want to be able to play around with this. I'm not exactly sure what voltage to drive this at, although obviously a higher voltage means we can drive it faster. We get more RPMs. Our motor is rated for 5,000. What's that? KVM? KPM? KV. So 5,000 kV, that means that if we have 1 volt, we can turn the motor at 5,000 RPM. We're going to ignore active demagnetization for now. Although it's probably something we need to understand. Using delay comp. This just tells me what this device does. The delay time is configurable. That's awesome. We can fix things in firmware later. Using the buck. So as I mentioned 20 minutes ago, the buck regulator components must be populated whether the buck is used or unused. So resistor mode should be configured by placing a 22 ohm resistor for RBK. So let's do that. This is RBK. I can even call it as such. So RBK, and that value is 22. And a 6.3 volt rated 22 microfarad capacitor. Okay. The footprint for that resistor, I'm just going to keep using our friend R0402 unless told otherwise. So there, done. Here, footprint doesn't matter, but we do need the 22 microfarads. 22, not C1, we're going to call this CBK. And its footprint and C42. I don't see that being realistic. Why not? Description. 6.3 volt. 6 point, what does it say? 6.3 volt rated. Rated. Cool. Go here. Again, just make sure everything's hunky dory. Yeah, you can't. A few of the footprints aren't assigned. That's fine. Okay, so we don't have to care about if the load requirement is less than 40 milliamps. Ensure the resistor is rated for the power dissipation required for the worst case VM voltage dropout. So we do need to worry about this. Calculate the resistor power rating required for 24 volt rated system. So we're looking at a 17 volt rated system, 3.3 output, and a 20 milliamp load current, but it's not loaded, so we don't care, right? Like, if we have nothing connected here, so it would just be whatever voltage is at this SW point minus the voltage at ground divided by that resistance. What is the voltage at SWBK? So let's have a quick gander. So we're on 85 right now. We'll come back. Put a pin functions SW. It is the buck switch node. Connect this pin. Okay. And what voltage is that node normally at? So let's go to the buck section here. So we're on the resistor side, SPI device, yes. And it says that the typical is 3.3, depending on the buck selection. So what was that? That was the buck regulator average voltage. This is the buck regulator average voltage. Well, that was for the SPI device. This is for the hardware device, where SPI. This is the ripple. External buck regulator load. Here, 40 milliamps. And can I disable it? 40 minus IAVDD. Well, IAVDD. Yeah, we should probably still pick a resistor that can deal with that kind of wattage. I mean, how many watts can a normal resistor deal with? How many watts does... What am I asking now? Let's just go to DigiKey. Products. Resistor. Not bad. Okay, 8 minutes, and then I'm getting the hell out of here. 3 views, nice. So, this is a 0.1, so 100 milliwatts. And we're looking for about 400 milliwatts. So how much would it cost for something that has that 400 milliwatt? Let's go, let's clear that, go here, all the way down from here. I think we'll be fine if we go something a little lower, but let's apply in stock. So you can still get pretty cheap, 0.16, cool. Done. Okay, so I think we'll need to set this up to be 84, right? Like that. So it's at 40 milliamps. So in the no load case, it's at 40 milliamps minus the current being fed through AVDD. AVDD is going to be like 5 milliamps. So I'd say like it's almost 40 milliamps total. So it's a 17, which is the max voltage that that 4S battery would get to, although I'm probably going to end up using 3S. 17 minus 3v3, and then we're going to multiply that by 40 milliamps. That doesn't sound right. Resistor mode allows for power to be dissipated in an external resistor if the load requirement is less than 40 milliamps. Yes. Ensure the resistor is rated for that. This doesn't seem right. I think a 500 milliwatt is fine. You know, when your spidey senses are tingling, I definitely need to get off. All right, 5 minutes. So we're gonna do a 0.5 watt here. Unsaved, cool. So the comments don't actually mean that I've gone ahead and done that, but it will be a reminder for me later. So cool, done that, done that. What else am I doing? Participation, that is dissipation. Okay, cool, cool. So we need to worry about bulk capacitance. The inductance between the power supply and the motor drive system limits the rate current can change from the power supply. If the local bulk capacitance is too small, the system responds to excessive current demands or dumps from the motor with a change in voltage. When the adequate bulk capacitance is used, the motor voltage remains stable and high current can be quickly supplied. So generally provides a recommended value, but system level testing is required. Okay, I see. Motors, drive system, IC bypass, and local bulk capacitor. So the bulk capacitor, I suspect, is this 10U. So it is not unpolarized. That's a lie. So go here. Oh, well, let's change that symbol up. Add polarized. Polarized. There you go. Boop. I don't need it to say that though. Go here, 10 footprint. Lord, if I know, we'll just pick these, but it's going to be one of the electrolytic capacitors that we can fold over, so not a surface mount. These are all surface mount. Yeah, here you go, through hole, axial. I don't know, man. It shouldn't need to be that big. I can pick this for now. Why is it? Normally they would have two holes. Here, I'll show you, sorry. Normally they would have two holes side by side, but right now it's one hole on one side, one hole on the other, and I don't like that. What's going on? Radial, no. I think radial. So this probably makes the most sense. We get radial, and then we just stick it in the hole and bend it over. But there should be like silkscreen footprints that show that exact scenario. Disc. Might need to make our own footprint if you want to be real swanky with it. This is still capacitor, and then yeah, we're done. So I don't know. I'm just gonna pick a Vichy. axial. Like what the hell is an axial capacitor? Eh. 2 minutes. Capacitor. Yeah. So why is it giving me one there and one there? What's wrong with you? Oh, let's see. There you go. That makes more sense. So there's one on either side. I don't deal with these kinds of resistors all that often, so we're gonna go with a radial. Then we'll just bend it over. The smallest one for now. Done. All right. For us, see how big that is. I love this. So yeah. So and we'll have that supply closer to the battery lead, so somewhere around here. Good for us. And just for your viewing pleasure, we're going to end off with this 3D model. This is what she's going to look like roughly. The word outline is missing or malformed. Your outline is malformed. Let's run DRC quickly. There you go. What do you want? Nope. Where? There. Does not like that. It's not my fault. I didn't design this. TI. Okay. Well. The board has malformed outline. No edge cuts. That makes sense. Alright, I'm using Courtyard. What if I do this? Edge cuts. Done. And now I do DRC, or let's do 3D model. Ooh, so nice. Okay, cool. So, not the prettiest thing, but we've made a lot of progress. So what I'm going to do to end off, go to PowerShell, get and check what we have made. So we modified the schematic MPCP, so we're going to add those. Commit, and our message will be, where are we right now? So motor driver is, say driver is 60% complete. The mic controller is, it's at 30%. I'm not pushing that. This is just me keeping track locally. All right, all done. Thank you so much for tuning in. I love you. We'll talk soon. Bye-bye.